Everything we love, everything we build, everything we believe will last, eventually collapses. The stone walls of castles crumble into dust. The brightest stars run out of fuel and fade into darkness. Civilizations rise in glory, then vanish into silence, leaving behind little more than fragments of pottery or ruins swallowed by vines. We may tell ourselves that progress marches forward, that human ingenuity secures permanence. But underneath it all, there is a quiet whisper, an invisible law, a shadow written into the very mathematics of existence. That law is entropy. Entropy is not dramatic like fire or storms, not immediate like earthquakes or floods. It doesn't announce itself with violence. Instead, it works silently, inescapably, constantly. It is the soft fraying of fabric, the fatting of photographs, the cooling of coffee left on the table. It is the reason our bodies age, the reason our memories blur, the reason time feels like it only moves in one direction. Entropy is not just one rule among many. It is the rule that underlies the very flow of reality. And yet here we are, creatures of order, creatures of memory, trying desperately to hold back the tide. We embalm kings, we carve monuments, we archive knowledge, we imagine eternity, but entropy always wins. The mummies decay, the statues weather, the books turn brittle. The digital files stored in the cloud will eventually lose their meaning once the machines that hold them fall silent. In the grand equation of the cosmos, disorder is the default, and order is the brief rebellion. Why is this so? Why does the universe demand that everything fall apart? For most of history, humans thought of time as cyclical, the eternal return of seasons, the circle of life and death, the repeating patterns of myth and ritual. Permanence lay in the cycle itself. But entropy revealed something unsettling. Time is not a perfect circle. It is an arrow, and that arrow points toward decay. You cannot unspill milk, you cannot unburn wood, you cannot unlive a life. The very idea of irreversibility comes from this invisible force. Entropy is, in a sense, the universe's accountant. It keeps the balance sheets of energy. No matter how cleverly energy is transformed, how efficiently it is used, there is always a loss, always a drift toward disorder. When steam engines first powered the Industrial Revolution, scientists noticed this stubborn loss of useful energy. What they discovered was not simply a quirk of machines, but a truth written into the cosmos itself. It was as though the universe had rules not just for motion, but for destiny. The haunting power of entropy lies not only in physics but in philosophy. We humans long for permanence. We imagine heaven, immortality, digital legacies, and eternal civilizations. We invent myths of renewal, rebirth, and cyclical return to comfort ourselves. But entropy speaks otherwise. It tells us that permanence is an illusion, that even the mountains will erode, that even the stars will fade, that even time itself has a story of running down. To confront entropy is to confront the fact that the universe itself is not built to last. It is built to unravel. And yet, paradoxically, within that unraveling lies beauty. The cherry blossom is beautiful not because it lasts forever, but because it falls. The sunset moves us not because the sun will shine eternally, but because it sinks below the horizon and reminds us of the fleetingness of light. Entropy, in this way, gives meaning to impermanence. It is the shadow that makes the flame visible. Without entropy, perhaps nothing would change, nothing would age, nothing would die. And without death or change, could there be life or love or story at all? But beauty cannot erase the chill of inevitability. Stand beneath the night sky and remember that every star you see is dying. Our sun is slowly, imperceptibly, burning through its nuclear fuel. In 5 billion years, it will swell into a red giant and consume the Earth before shrinking into a cold white dwarf. Galaxies collide, black holes evaporate, and the great drama of creation is in fact the slow work of entropy spreading energy thinner and thinner until nothing remains but silence. The universe is not winding up, but winding down. This vision is unsettling, but it is also profoundly humbling. Entropy reminds us that we are temporary guests in a temporary cosmos, that every act of creation we attempt, art, love, discovery, is set against a backdrop of inevitable loss. But far from diminishing their value, entropy magnifies it. For if everything were permanent, then nothing would matter. It is precisely because time runs forward, because things fall apart, that our lives burn brightly with urgency and meaning. Still, the human mind resists. We do not easily accept that the story ends in decay. We look for loopholes, exceptions, miracles. Some imagine technologies that will defeat aging. Others imagine civilizations that escape into digital eternity. Some physicists imagine universes that reboot themselves, rising like phoenixes from cosmic ashes. In every case, we are driven by the same impulse: to deny entropy, whisper to say, "Not me, not us, not this." And yet, the second law of thermodynamics has never been broken. It is the closest thing physics has to absolute truth. It applies in every laboratory, in every corner of the cosmos. It does not yield to desire or effort or faith. This is why entropy is not merely a scientific principle. It is a philosophical confrontation with fate itself. But what truly is entropy? Is it disorder? Is it randomness? Is it the loss of energy or the loss of information? Why should the universe prefer chaos to order, silence to music, dust to stars? These are not idle questions, but profound mysteries. Entropy is not simply a fact, it is a riddle. And to solve it, we must journey deep into the heart of physics, into the very foundations of time, energy, and reality. This is where the story now turns. We will peel back the history of discovery, from the steam engines of the 19th century to the equations of modern cosmology. We will see how entropy reshaped our understanding of time, of life, of the universe itself. And in that journey, we will confront the possibility that entropy is not just the law of decay, but the very principle that gives shape to existence. The castles may crumble, the stars may die, civilizations may vanish, but in their unraveling lies the great secret of reality. Entropy whispers always, and if we dare to listen, it will tell us the story of everything. If the first section introduced entropy as the whisper of collapse, then here we step into the chamber where that whisper first became a law. To understand entropy, we must step back into the heart of physics, where energy, motion, and time reveal their deepest secrets. Entropy does not stand alone. It is part of a family of laws that govern the universe with such consistency that physicists call them the laws of thermodynamics. These laws are not inventions but discoveries, mathematical fingerprints left by the universe, showing us how reality truly works. The first law is comforting. Energy cannot be created or destroyed. It can only change forms. A candle burns, releasing chemical bonds into light and heat. A river flows, turning turbines into electricity. A star fuses hydrogen, converting mass into radiant energy that crosses the emptiness of space. This law suggests balance, permanence, even a sense of cosmic fairness. Energy never disappears, it only moves. But then comes the second law, and with it, the shadow. The second law of thermodynamics tells us that while energy is conserved, its usefulness is not. Energy inevitably disperses, degrades, spreads out. A hot cup of tea left on a table will cool to room temperature. A gas released into a chamber will fill it evenly. A machine will lose efficiency to friction and heat. In every case, the available energy for doing work decreases. This creeping loss is what we call entropy. Not the disappearance of energy, but the loss of its order, the slipping away of structure into randomness. This is why entropy feels like the enemy of permanence. It's not enough that energy continues to exist. It drifts into states where we cannot harness it. Entropy is the spreading of possibilities, the smoothing of differences, the surrender of structure to disorder. Left unchecked, it guarantees that any system, whether a teacup, a planet, or a universe, tends toward equilibrium, the bland state where no more work can be done, where motion ceases and time itself loses direction. The contrast becomes clearer when we consider Newton's clockwork universe. In Newton's equations, time runs symmetrically. Reverse the velocity of every planet and the system could run backward, perfectly mirroring its forward motion. Newton's laws do not care about yesterday or tomorrow. They only describe how objects move when forces act. In that classical world, time is reversible. Nothing forces it in one direction. But our lived experience tells a different story. Memories accumulate in one direction, never the other. Milk spills on the floor but never gathers back into the glass. We age but never unage. Here enters entropy, the true arrow of time. Entropy gives time its asymmetry. Without it, the future and the past would be indistinguishable. Imagine a film of billiard balls colliding on a table. Play it forward or backward and you may not know the difference. But now imagine a film of ice melting into water. Play that backward and it instantly looks absurd. Entropy is the reason. It ensures that melting happens in one direction only. This is the paradox at the heart of physics. The microscopic laws of motion are reversible, but the macroscopic world we live in is irreversible. Entropy is the bridge between those two realities. But what is entropy really? At first, it was described as wasted heat, the part of energy that could not be turned into work. Later, Ludwig Boltzmann gave it a deeper meaning. Entropy is the measure of the number of possible arrangements in a system. The more ways a system can be configured, the higher its entropy. A deck of cards perfectly ordered by suit and rank has low entropy. Shuffle the deck and the entropy rises. Each shuffled state is equally possible, but only one corresponds to perfect order. Disorder is simply more probable than order. This is the cruel mathematics of existence. It is not that order is impossible, it is that disorder vastly outnumbers it. This probabilistic insight reframes entropy not as a villain, but as inevitability. Systems naturally drift toward the most probable state, just as dice tend toward randomness when rolled again and again. Entropy is the mathematics of probability written across the cosmos. It explains why order is fragile, why patterns collapse, why equilibrium is the final destination of all systems. And yet this bleak inevitability hides a strange wonder. Entropy is also the reason stars shine, rivers flow, and life itself can exist. Energy moves from high concentration to low, from hot to cold, from ordered to disordered. But in that very movement, work is done. The earth is bathed in sunlight because the sun is dissipating its energy outward. Plants grow, animals live, and civilizations rise on the flow of that energy from concentrated to dispersed. Entropy ensures decay, yes, but also motion, transformation, and story. Without entropy, there would be no time, no change, no life. This is the profound contrast entropy offers. It is both the destroyer and the creator. It tears down order but also fuels the processes that build it temporarily. It defines the forward march of time, yet allows brief eddies of complexity to arise against its current. Life, in this sense, is entropy's paradox. We are patterns of improbable order sustained by the consumption of energy gradients. Every breath we take, every meal we eat is entropy at work, reshaping order into disorder, even as it allows us to persist. Entropy is the silent director of the cosmic play, determining not only the acts but the very direction in which the play unfolds. It does not scream for attention, yet everything that exists bows to its rule. Stars, galaxies, empires, all follow the arrow it sets. Time's arrow is entropy's arrow, and though Newton's equations may allow for reversibility, our world insists otherwise. Entropy is the reason the future feels open and the past feels closed. If this feels unsettling, it should. Entropy denies the possibility of perfection, permanence, or escape, but it also gives us a framework to understand why things happen the way they do. Why ice melts, why stars die, why history has direction. Entropy is not merely the principle of disorder, it is the architecture of reality itself. And so we arrive at a turning point. Having glimpsed entropy as the architect of time and change, we now must ask, how did humans first discover this invisible law? Where did we first notice its whisper? It was not in the heavens or in the abstract equations of philosophers. It was in the smoke of factories, the pistons of steam engines, the hum of machines that drove the Industrial Revolution. It was in our attempt to harness fire and motion that we first uncovered the mathematics of decay. In the next chapter, we travel to the 19th century, where inventors, engineers, and scientists sought to master energy, only to stumble upon entropy's truth. It is a story of ambition and humility, of discovery born not from philosophy but from the practical need to make engines work better. In their struggle for efficiency, humanity discovered the law that governs destiny. The story of entropy's discovery is not one of philosophers gazing at the stars or mystics pondering eternity. It begins instead with something more ordinary, more practical: the quest to make engines run better. In the 18th and 19th centuries, as coal-fed furnaces and iron rails stitched continents together, steam became the lifeblood of civilization. But engineers noticed a troubling truth. No matter how they refined their machines, no matter how carefully they crafted pistons and boilers, there was always waste. Some energy always slipped away. Steam cooled, metal heated, motion lost its vigor. The dream of a perfectly efficient machine proved impossible, and it was in this stubborn failure that science caught its first glimpse of entropy. Enter Sadi Carnot, a French military engineer who in 1824 wrote a slim book that would change physics forever. Carnot wanted to understand how to extract the maximum useful work from heat engines. His thought experiments were elegant. Imagine an idealized engine, perfectly insulated, perfectly balanced, operating in cycles. Even in such perfection, Carnot showed, efficiency had an upper limit. Heat could never be fully converted into work. Some must always be released to a cooler reservoir. This was not just an engineering inconvenience. It was a universal principle. In every transfer of heat, there is an unavoidable loss of potential. The Carnot efficiency became the ceiling of possibility. Behind it lay something more profound, the hint of a law that would govern the cosmos. Decades later, Rudolf Clausius, a German physicist, gave this elusive principle a name. In 1865, he introduced the term entropy, derived from the Greek word tropine, meaning transformation. Clausius declared, "The entropy of the universe tends to a maximum." With those words, entropy was no longer about engines alone, it was about everything. Clausius captured in mathematics what Carnot had glimpsed in imagination. Energy may be conserved, but its usefulness always diminishes. The universe itself was subject to this hidden erosion. Clausius's insight spread like fire through physics. What began as practical tinkering with steam engines became a revolution in our understanding of reality. Heat was not simply a mysterious fluid, as some still believed, but the motion of countless unseen particles. Every collision, every vibration, every microscopic jostle carried with it the seeds of disorder. To speak of entropy was to speak of the statistics of the unseen. This is where Ludwig Boltzmann enters the story. In the late 19th century, Boltzmann sought to give entropy a deeper foundation. He saw entropy not just as wasted heat but as probability made manifest. The more ways particles in a system could be arranged, the higher its entropy. Order was simply rare, fragile, unlikely. Disorder was overwhelmingly probable. His famous equation, engraved on his tombstone, S equals K log W, linked entropy S to the number of possible microstates W, with K as Boltzmann's constant. It was a profound shift. Entropy was not a curse or a mystery but a matter of counting possibilities. The universe's march toward disorder was not malicious. It was statistical inevitability. And yet Boltzmann's genius was met with skepticism, even ridicule. Many of his contemporaries doubted atoms even existed. To them, his statistical mechanics seemed like fantasy. Boltzmann carried the weight of criticism heavily, and his tragic suicide in 1906 remains one of science's great heartbreaks. Only later, with the rise of atomic theory, would his brilliance be vindicated. Today, his equation is a cornerstone of physics, his insight a lens through which we view the unfolding of time. What makes this history haunting is how human ambition uncovered its own limits. Engineers wanted better locomotives, more powerful engines, greater control over fire. What they found was not mastery but humility. Nature revealed an absolute law. You may build, you may harness, you may refine, but you cannot escape entropy. No empire of coal or steel, no revolution of industry could conquer the mathematics of disorder. Think of the contrast here. Humanity surging into modernity, railroads carving landscapes, factories roaring with power, and underneath it all, an invisible current of decay. Every locomotive that thundered forward also spread entropy into the world. Every factory that lit up the night also released heat and disorder into the air. Progress was inseparable from entropy's toll. Civilization itself became an engine, running not just on coal but on the law of entropy. This truth extends far beyond machines. Entropy governs not only engines but all processes of transformation. It tells us why perpetual motion machines are impossible, why no system can run forever without loss. It tells us why the Earth, bathed in sunlight, can grow forests and civilizations only because the sun itself is burning down its store of fuel. It tells us why our bodies, too, must consume and excrete, metabolize and decay. Entropy is the universal accountant, tallying every exchange, ensuring that order is always borrowed, never owned. The beauty of this discovery lies in its universality. What began with the hiss of steam and the clang of pistons grew into a principle that spans the cosmos. Entropy explains why stars radiate, why planets cool, why galaxies evolve. It even reaches into philosophy, shaping our sense of time and meaning. From Carnot's engines to Clausius's equations to Boltzmann's probabilities, entropy emerged not as a quirk of machines but as the hidden rhythm of reality. Consider the poetic irony. Humanity, in its pursuit of mastery over nature, discovered the very law that limits mastery. We sought control, but we found inevitability. We built machines to conquer time and distance, and in the process uncovered the arrow of time itself. The Industrial Revolution promised progress without end, but entropy reminded us that every advance is purchased at the cost of spreading disorder. In seeking efficiency, we discovered fate. And so, the story of entropy's discovery is more than scientific, it is existential. It shows us that truth often hides in failure. The impossibility of perfect engines became the key to understanding the imperfection of the universe. The dream of perpetual motion collapsed, and in its ruins, the second law of thermodynamics was born. Entropy became the law not just of machines, but of memory, mortality, and meaning. From here, the stage is set to broaden our view. We have followed entropy from steam engines to universal law, but now we must confront its implications for our deepest intuitions about time itself. For if entropy governs the flow of energy, it also governs the flow of history. If entropy explains why engines run down, it also explains why moments cannot be reversed, why time itself has direction. Entropy, it turns out, is not merely the physics of heat. It is the physics of becoming, the mathematics of irreversibility. In the next chapter, we leave the clanging of factories and the notebooks of engineers. We step instead into the philosophical realm, where entropy ceases to be merely about machines and becomes the very arrow of existence. We will explore how entropy shapes not only engines and stars, but memory, identity, and the meaning of time itself. For the whisper of disorder is not only in steam, it is in every heartbeat, every thought, every passing moment. We live in a world where time feels natural, obvious, and unquestionable. We wake, we age, we remember the past but never the future. We speak of before and after as if they were carved into the fabric of reality. Yet the deeper we look into the equations of physics, the stranger time becomes. For most of physics, time has no preferred direction. The equations work just as well forward as backward. In theory, the dance of particles could just as easily rewind as play out. And yet we never see glasses unshatter, smoke gather back into a candle flame, or ourselves grow younger. The forward march of time is real, and entropy is its drumbeat. Entropy is what gives time an arrow. Without it, the future and the past would be indistinguishable. Consider Newton's mechanics. If you knew every position and velocity of every particle, you could run the equations backward and predict the past just as accurately as the future. Determinism, in this sense, is time neutral. But the universe we inhabit does not feel neutral. It feels irreversible. Entropy explains why. The probability of particles arranging themselves into disorder is overwhelmingly higher than into order. The future is simply the direction in which entropy increases. The arrow of time is the arrow of entropy. This becomes clearer when we reflect on memory. Why do we remember yesterday but not tomorrow? Our brains are physical systems, encoding information in fragile arrangements of neurons. To remember something is to preserve low-entropy structures against the tide. But recording memory itself produces entropy. It requires energy, chemical activity, and heat. The act of remembering is itself irreversible. We cannot remember the future because entropy has not yet written it. Our sense of past and future is not merely psychological. It is physical, carved by entropy into the fabric of experience. Aging is another example. Biologically, organisms are engines of temporary order, fueled by energy flows. But no matter how efficient, no body can escape the slow accumulation of disorder. Cells misfire, DNA mutates, proteins tangle. Entropy leaves its fingerprints on every wrinkle, every faded memory, every heartbeat that cannot be rewound. We may dream of immortality, but entropy defines mortality as the natural consequence of time's asymmetry. And yet contrast this with Einstein's theory of relativity. In relativity, time is flexible, a dimension woven with space. The block universe interpretation even suggests that past, present, and future all exist equally as slices of spacetime. In such a view, there is no privileged now, no cosmic clock ticking forward. All events are laid out timelessly. But this clashes with our visceral sense of becoming. If all moments exist at once, why do we feel time flow? Why do we live in the present rather than across the whole of spacetime? Here entropy enters again, not as an opponent to relativity but as a complement. Relativity describes the geometry of spacetime. Entropy describes its direction. Without entropy, relativity would leave us in a frozen block where nothing truly happens. With entropy, the block comes alive, each slice stacked into history, each moment emerging from the one before. Entropy is what transforms static spacetime into lived experience. It is the difference between a photograph album and a film. The album preserves all moments equally, but only the film has direction, story, and unfolding. Philosophically, this raises profound questions. If the arrow of time is born from entropy, then meaning itself is tied to disorder. Narratives exist because beginnings differ from endings. Memory exists because the past is distinct from the future. Morality, choice, identity. These depend on the idea that what we do now shapes what comes later. Without entropy, without the arrow, life would lose coherence. Existence would flatten into a meaningless simultaneity. But this realization also unsettles. If entropy defines time's flow, then the story of the universe is one of inevitable decline. The past is ordered, the future disordered. Every moment of meaning carries within it the seed of loss. Entropy gives us the arrow, but the arrow points toward decay. This tension between the necessity of entropy and the tragedy of its outcome is at the heart of the human condition. And yet within this tragedy lies paradoxical beauty. Entropy creates time, but it also makes possible the emergence of complexity along the way. Stars form, burn brightly, and collapse. Life arises on the flow of energy, resists disorder for a time, and fades. History unfolds, art is created, civilizations rise and fall. The arrow of time is not a monotone descent but a melody, moments of improbable order blooming against the background of decay. Our lives, brief though they are illuminated precisely because they occur along this one-way path. Contrast this with a hypothetical universe without entropy. Imagine time flowing but reversible, every event as likely to unwind as to proceed. In such a world, no memory would stick, no story would unfold, no arrow would give life its urgency. Nothing would matter because everything could be undone. Entropy makes experience meaningful by making it irreversible. The pain of loss, the sweetness of love, the urgency of decision, all these draw their intensity from entropy's arrow. We cherish moments precisely, because they cannot be repeated. And so, entropy is not only physics, it is philosophy. It forces us to accept impermanence, to recognize that history is written in one direction only. It reminds us that every action once taken shapes a future that cannot be erased. This is terrifying, but it is also liberating. Entropy tells us, this moment matters because it will never return. The philosopher Augustine once asked, "What is time?" and confessed that when he tried to define it, he did not know. Modern physics gives us an answer, but not a comforting one. Time is entropy's unfolding. To live in time is to live in the midst of irreversible transformation. The arrow is what makes us mortal, but also what makes us human. Still, questions remain. If entropy drives time forward, why did the universe begin in such a low entropy state? The Big Bang appears to have been an explosion of astonishing order, from which entropy has been rising ever since. Why should the cosmos start ordered only to unravel? What set the arrow in motion? These mysteries remind us that entropy, though understood in equations, is not fully explained in essence. And this leads us to the next puzzle: life. For if entropy rules the universe with an iron law of disorder, how do living beings emerge and persist? Why do we see complexity, growth, and flourishing in a universe fated to decay? Are we illusions of permanence, bubbles of temporary order riding on the current of entropy, or is there something deeper at play? In the next section, we will turn to the paradox of life itself, how organisms seem to resist entropy, how order arises in defiance of disorder, and why this resistance is not a violation but a deeper expression of entropy's law. For now, we leave with this truth: the arrow of time is real, and entropy is its guide. Everything we know, everything we love, every story we tell exists because time flows one way. Entropy makes the world mortal, but it also makes it meaningful. At first glance, life seems to mock entropy. Walk through a forest and you will see not disorder but astonishing design. Trees branching into fractal patterns, leaves aligning to catch sunlight, ecosystems balanced in intricate harmony. Look into a microscope, and you find DNA strands encoding precise instructions, cells coordinating thousands of chemical reactions per second, proteins folding into elaborate shapes that fit like keys into locks. In the human brain, billions of neurons fire in exquisite synchrony to produce thought, memory, and imagination. Everything about life suggests order, growth, and complexity. It is as if, in defiance of the second law of thermodynamics, life is a rebel against disorder. And indeed, for centuries this is how it seemed. How could the relentless march toward decay possibly explain the flourishing of gardens, the elegance of mathematics, the music of Bach, the laughter of children? Entropy tells us that systems tend toward randomness, yet life seems to evolve toward greater sophistication. The arrow of time points toward decay, yet living systems climb upward, building new levels of complexity with each generation. Is life an exception? Has nature carved out a loophole in its most unforgiving law? The answer, as it turns out, is both yes and no. Life does not break the law of entropy, it expresses it. To see how, we must look more closely at what entropy really governs. Entropy applies to closed systems, systems isolated from their environment with no energy flowing in or out. But life is not closed, it is open. Every organism, from a single bacterium to a sprawling rainforest, exchanges energy with its surroundings. A plant absorbs sunlight, an animal eats food, humans burn fuel. In each case, life maintains local order only by increasing disorder elsewhere. This is the great secret. Life does not escape entropy. It survives by channeling it. When we breathe oxygen and consume food, our bodies transform chemical energy into the improbable order of growth, repair, and thought. But in doing so, we release heat, waste, and disorder into the environment. The net entropy of the universe always increases. Life's apparent defiance is a mirage. We are not fighting the tide. We are riding it, carving delicate structures in the foam even as the current sweeps us toward dissolution. Think of a refrigerator. It keeps its interior cool and ordered, slowing the decay of food. but open the back and you will find heat pouring out. The refrigerator creates local order only by generating more disorder overall. Life is the same. We are self-organizing islands in a vast sea of entropy, but our survival depends on throwing entropy outward. Every moment of beauty, every breath, every thought is purchased at the price of greater disorder somewhere else. And yet this only deepens the mystery. If entropy inevitably wins, how does life manage to sustain itself at all? The answer lies in gradients. Entropy drives energy from areas of high concentration to low, hot to cold, ordered to disordered. The sun is a furnace of concentrated energy. Earth is a cooler basin. Between them flows a river of usable energy, a current that life has learned to harness. Plants catch photons, transform them into chemical bonds, and form the foundation of food chains. Animals eat plants, predators eat prey, and humans sit at the top of this energy cascade, building cities, writing books, and launching rockets. All of it depends on the steady burning of the sun, the flow of energy from hot star to cool space. Without that flow, life would wither. Entropy enables life not by breaking its law, but by creating the gradients that make life possible. This perspective transforms our understanding of evolution. Evolution is not a story of escaping entropy. It is a story of exploiting it. Organisms evolve to capture and use energy more effectively, to sustain improbable order for longer before dissolving back into disorder. Life is entropy's most intricate performance, not its rival. Even consciousness, the most mysterious feature of life, can be seen as a form of entropy management. Our brains consume vast amounts of energy, converting fuel into patterns of thought. In doing so, they create immense amounts of entropy, released as heat. Thought itself is not free, it is costly. To be conscious is to burn through order at a furious rate. This raises a haunting possibility. Consciousness, which feels like our highest achievement, may simply be another way the universe disperses energy. Our sense of meaning, our pursuit of knowledge, our search for permanence. These may be side effects of entropy's law, patterns briefly carved in energy flows that ultimately fade into randomness. If so, then consciousness is not the defiance of entropy but its masterpiece, the most complex, transient flame ever kindled by disorder. And yet this perspective does not diminish life. It elevates it. To see life as entropy's paradox is to recognize its fragility, its improbability, its brilliance. A flower blooming, a child learning, a civilization rising, these are not illusions but miracles made possible by entropy's current. Like whirlpools in a river, they appear stable, even beautiful, but they exist only because the river flows. Without entropy, without the drive from hot to cold, there would be no whirlpools, no blooms, no thought. Life is entropy dancing with itself, spinning brief moments of order in the vast unraveling of time. This contrast, life as both fragile and magnificent, touches philosophy as deeply as biology. We may mourn entropy as the destroyer of permanence, but it is also the condition for possibility. Without entropy, no stars would shine, no energy would flow, no life would emerge. Entropy is not only the force of decay, but also the midwife of creation. Life is the paradoxical gift of a universe fated to end. But this paradox unsettles. If life is only temporary order purchased by greater disorder, does that strip it of meaning? Are we merely entropy machines, briefly burning bright before fading into equilibrium? Or does the very transience of life make it meaningful? Perhaps permanence was never the point. Perhaps the arrow of time, powered by entropy, gives urgency and depth to existence. We do not live forever, but we live now in this fleeting moment, in this fragile rebellion against chaos. This is why philosophers and scientists alike have struggled with entropy not only as physics but as metaphor. It explains aging, death, and decay, but it also explains growth, evolution, and complexity. Entropy is the law of endings, but it is also the condition for beginnings. We live because the universe dies. We think because stars burn. We dream because energy flows. The story of life, then, is not a story against entropy, but with it. Every heartbeat, every breath, every act of creation is a momentary victory, a local reversal sustained by energy borrowed from elsewhere. These victories cannot last, but they matter precisely because they are temporary. Entropy guarantees the loss of permanence, but it also ensures the significance of impermanence. We love, we create, we struggle not in spite of entropy but because of it. And yet there is more to say. For entropy is not only about heat and energy, it is also about information. The same mathematics that describes disorder in particles also describes uncertainty in knowledge. Just as energy spreads, so does information degrade. Entropy does not only touch the physical, it touches the mental, the digital, the informational. If life raises the paradox of resisting disorder, information raises an even deeper paradox. Can knowledge itself decay? Does the universe not only age and die, but also forget? This is where we must go next. From the biological to the informational, from the entropy of bodies to the entropy of knowledge. For if entropy governs energy, and if it shapes life, then perhaps it also rules thought itself. And if that is true, then the story of entropy is not only about the fate of stars and organisms, but the fate of meaning itself. When we think of entropy, we imagine heat cooling, stars burning out, or matter collapsing into dust. But in the 20th century, entropy acquired a new and startling identity, one that shifted it from physics into the very fabric of thought, language, and knowledge itself. Entropy was no longer only about energy. It was about information. The bridge was built by Claude Shannon, a quiet mathematician working at Bell Labs in the 1940s. Shannon was trying to solve a practical problem, how to send messages efficiently through telephone wires. But in seeking efficiency, he uncovered something profound. Shannon realized that communication is not simply about words or meaning, it is about uncertainty. Every time we send a message, the recipient must distinguish between possibilities. A coin toss has two outcomes, each equally likely. The uncertainty is one bit. The more uncertain a message, the more information it carries when revealed. Shannon called this measure of uncertainty entropy. It was no accident he borrowed the term from physics. Just as physical entropy measures the disorder of particles, informational entropy measures the unpredictability of symbols. A string of random letters has high entropy. It is hard to predict. A repetitive string like AAA has low entropy. It is easy to guess. Information, in Shannon's insight, was not the opposite of entropy but bound to it. The more uncertain, the more potential for information. This was revolutionary. It meant that the mathematics of thermodynamics could also describe the mathematics of communication. Entropy became the hidden code linking heat, energy, and knowledge. Suddenly, the boundaries between physics and information blurred. Was the universe merely a machine of matter and energy, or was it also, at its core, a processor of information? The implications multiplied. In physics, entropy measures how many microscopic states correspond to a macroscopic system. In information theory, entropy measures how many possible messages could arise from a source. The symmetry is uncanny. Both are about possibilities, probabilities, and uncertainty. Both describe the spread of order into disorder. Both suggest that entropy is not about things, but about knowledge of things. In a sense, entropy is ignorance quantified. This perspective reframes some of the universe's greatest mysteries. Consider the black hole. When matter falls into a black hole, it seems to vanish. The black hole swallows it, sealing it behind an event horizon from which nothing escapes, not even light. But what happens to the information contained in that matter? If entropy is linked to information, then information cannot simply be destroyed. Physics forbids it, yet black holes seem to erase it. This tension became the black hole information paradox, a puzzle that still haunts physicists. Stephen Hawking deepened the paradox in the 1970s when he showed that black holes are not eternal. They emit faint radiation, now known as Hawking radiation. Over unimaginable timescales, black holes can evaporate. But as they do, what happens to the information of everything they consumed? Does it vanish with them, violating the fundamental principle of physics that information must be conserved? Or is it somehow encoded in the radiation, hidden in subtle patterns? The debate continues. What is at stake is not merely astrophysics, but the very foundation of knowledge itself. If entropy is about information, then the universe is not simply decaying physically, it is also forgetting. Stars die, yes, but patterns, histories, identities may also erode. The idea that the universe loses not only structure but meaning is haunting. It suggests that entropy governs not only what happens, but what can be known. This idea resonates in our own experience. Memories fade, languages die, civilizations collapse and leave behind fragments that we struggle to interpret. The Library of Alexandria burned, and with it, countless scrolls vanished forever. Information, like energy, disperses. It becomes corrupted, degraded, uncertain. The entropy of culture mirrors the entropy of physics. And yet, just as life resists entropy by channeling it, so do humans. We write books, build servers, store data in DNA. We battle informational entropy with archives, backups, and memory. But even these are temporary. Servers fail, books rot, formats become obsolete. The whisper of entropy runs through every attempt to preserve knowledge. And yet here again, paradox emerges. While entropy destroys order, it also enables information to exist. If every message were perfectly predictable, no communication would be meaningful. If every system were frozen in perfect order, nothing new could be learned. Entropy, by allowing uncertainty, creates the possibility of discovery. In this sense, entropy is not the enemy of knowledge, but its condition. Without randomness, without surprise, there could be no information at all. This tension between entropy as destroyer and entropy as enabler runs through modern physics. Increasingly, scientists ask whether the universe itself is best understood not as matter and energy but as information. John Wheeler, the visionary physicist, famously declared, "It from bit." He meant that physical reality, it, may ultimately arise from binary choices, from bits of information. If this is true, then entropy is not just a physical principle, but the most fundamental law of existence. To measure entropy is to measure the possibilities of reality itself. This perspective transforms cosmology. The early universe, just after the Big Bang, had extraordinarily low entropy, a highly ordered state. As the universe expanded, entropy increased, but perhaps what was really increasing was not just disorder but information capacity. The universe was becoming capable of holding more distinction, more stories, more histories. Entropy as information growth paints a different picture. The universe is not just decaying, it is also recording. And yet the final horizon remains. If entropy continues unchecked, then eventually every gradient will flatten, every distinction blur, every bit of information degrade into noise. This is the vision of heat death, a cosmos in which no more information can be gained, where knowledge itself has dissolved into uniformity. It is the ultimate silence. Not only no stars, no life, but no difference, no message, no meaning. Entropy here becomes the erasure of story itself. Philosophically, this is both terrifying and profound. If the universe is information, then entropy is its editor, trimming, revising, erasing until nothing remains. But perhaps this too has meaning. Perhaps the fleetingness of information is what gives it value. A poem that survives for 1,000 years is precious precisely because it could have been lost. A memory cherished is precious precisely because it will fade. Entropy reminds us that knowledge is not infinite, it is fragile. And in that fragility lies beauty. Still, the paradox endures. If entropy erases, why does the universe also create? Why does order emerge at all? Why does life evolve? Why do civilizations record their histories? Perhaps entropy is not simply decline but transformation. Information is not lost but reshaped, encrypted in forms we do not yet recognize. Black holes may not destroy information but hide it in ways that stretch our imagination. The whisper of entropy may not be final silence, but a challenge to seek deeper codes. This is where science meets speculation. If the universe is fundamentally informational, then consciousness itself may be part of the puzzle. Our minds are processors of entropy, reducing uncertainty by making choices, creating meaning out of noise. Every act of thought is a small reversal of informational entropy, briefly carving clarity before it dissolves again. Consciousness may be not the opposite of entropy, but its collaborator. Entropy generating uncertainty, consciousness transforming it into meaning. And so we arrive at a new horizon. Entropy began as wasted heat, discovered in the pistons of steam engines. It became the arrow of time, shaping memory and mortality. Now it has become the hidden code of information, linking matter, energy, and meaning. The question before us is staggering. If entropy governs not only stars and engines but also knowledge and consciousness, then what does this say about the destiny of the cosmos? To answer, we must zoom outward. Beyond the scale of machines and minds, beyond the flow of messages and memories, lies the universe itself. Stars burning, galaxies colliding, black holes evaporating. Entropy is not only a law of knowledge but a law of cosmic destiny. To follow its trail is to confront the ultimate fate of all things. Stand beneath the night sky and what you see feels eternal. The stars seem endless, steady, reliable. Ancient civilizations carved their myths and calendars into their patterns, trusting that the constellations would remain fixed long after their own empires crumbled. And yet, even the stars are dying. Every gleam in the sky is a furnace consuming its own fuel, a temporary beacon in the ocean of entropy. The cosmos itself is not exempt from the law of disorder. It is its stage. Entropy governs not only teacups cooling and forests aging, but the destiny of stars and galaxies. A star begins as a cloud of hydrogen gas. Gravity pulls the atoms together, heating them until nuclear fusion ignites. For millions or billions of years, the star burns steadily, converting hydrogen into helium, releasing torrents of light and heat. This energy flow creates the possibility of life, of planets, of stories. But fusion is not infinite. The hydrogen dwindles, the balance falters, and the star's life moves toward its end. Small stars fade into white dwarfs, glowing embers of what once was. Massive stars collapse and explode as supernovae, scattering heavy elements into the void. In either case, entropy has the final word. The concentrated fuel is spent, the order dissipates, and what remains is cooler, less useful, more disordered. Multiply this story by billions and you see the fate of galaxies. They shine brilliantly for ages, but their brilliance is borrowed time. Black holes at their centers feed on matter, stars burn out and gas clouds disperse. Over eons, galaxies lose their structure, their energy gradients flatten and their lights dim. The universe, in the grandest sense, is a theater of entropy. The act of creation, the formation of galaxies, stars, planets, is temporary order, brief flashes against the inevitable backdrop of disorder. The concept of heat death arises from this logic. If entropy always increases, then the universe is heading toward equilibrium. Equilibrium means no more gradients, no more flows of energy, no more work. It is the state where everything is uniform, where heat is evenly distributed, where no differences remain to drive motion. Imagine a universe in which every star has burned out, every black hole has evaporated, every atom is spread so thin across space that nothing interacts. This is not fire and fury, but silence and stillness. The cosmos dies not with an explosion, but with a sigh. This vision is chilling, but it also reveals the profound role of entropy in cosmic history. Without entropy, there would be no arrow of time, no burning stars, no chemical elements forged in supernovae, no life on Earth. Entropy drives the processes that create complexity, even as it ensures their eventual collapse. The stars we see are not eternal. They are temporary rebellions, bright moments born from gradients that entropy itself creates. The universe is not only unraveling, it is also composing a story along the way. Here lies the paradox. Entropy gives rise to order even as it destroys it. Galaxies form because matter clumps under gravity, releasing energy in the process. Planets cool, oceans circulate, weather patterns emerge, all driven by entropy's insistence on moving energy from concentrated to dispersed states. Life itself, as we have seen, is a local reversal carved from entropy's flow. These are not violations of the second law but expressions of it. Entropy creates the river. Complexity is the whirlpool that briefly dances within it. And yet the river flows toward the ocean of equilibrium. No matter how many whirlpools form, they cannot last. The lights of stars and galaxies will fade. Black holes, once thought eternal, will leak their energy away through Hawking radiation until they, too, vanish. The universe, in its vastness, is running down. Entropy ensures that the future will look less structured than the past. Still, there are mysteries here. Why did the universe begin in such a low entropy state? The Big Bang, as violent and chaotic as it sounds, was astonishingly ordered. It was a moment of extraordinary simplicity, from which entropy has been increasing ever since. Why should the cosmos start with such improbable order only to drift into disorder? Some physicists see this as one of the deepest unsolved riddles. Without an explanation for the low entropy beginning, the arrow of time itself remains mysterious. Speculation abounds. Perhaps our universe is one cycle in an endless chain, each new Big Bang resetting entropy. Perhaps entropy is not absolute but relative, and hidden dimensions or multiverses contain reservoirs of order we cannot see. Perhaps black holes, instead of being tombs of information, are gateways to new universes, each birth fueled by the death of another. These are not answers but attempts to grasp the enormity of entropy's horizon. For us, the implications are humbling. The stars above are beautiful precisely because they are mortal. The galaxies, magnificent as they are, will not endure. Entropy reminds us that the cosmos is not a static cathedral but a dynamic story, one with a beginning, a middle, and an end. To live in this story is to be part of a drama that spans billions of years, yet whose conclusion is written in the mathematics of disorder. But this story does not end in physics alone. If entropy governs stars and galaxies, what about civilizations? What about cultures, histories, and human ambition? Are we too subject to the same cosmic law? The collapse of empires, the erosion of memory, the fatting of achievements, these echo the entropy of stars. Human history in many ways is entropy written in culture. We rise, we build, we imagine permanence, but entropy ensures impermanence. In the next section, we will turn from the cosmic to the human. We will see how entropy not only shapes stars and galaxies, but also civilizations and memory. The entropy of physics becomes the entropy of history, revealing that the same law that cools stars also erodes empires. Entropy is not only the fate of the cosmos, it is the hidden driver of human destiny. Entropy is not confined to stars and galaxies. It whispers through human history, shaping the rise and fall of civilizations as surely as it shapes the burning of suns. Though we rarely call it by name, entropy is the silent partner of every empire, the quiet undertow beneath every triumph, the current that pulls all human efforts toward eventual decline. To see this, we need only look at the ruins that scatter the earth, each one a monument to entropy's hidden rule. The Roman Forum, once a heart of empire, now lies in fragments. The Mayan temples, once alive with rituals and calendars of the stars, are overgrown with jungle. The cities of Mesopotamia, once bustling with trade and invention, are little more than dust beneath desert sands. These ruins are not just relics of political missteps or invasions, they are the signature of entropy. Human societies, like stars, rise by consuming energy, food, fuel, resources, and as they grow, they generate disorder. They export entropy to maintain local order, but eventually the gradients falter. The resources dwindle, the structures weaken, and collapse follows. Consider agriculture, the foundation of civilization. To cultivate fields is to impose order on the wild, but each harvest drains nutrients from the soil, requiring labor and energy to replenish. Irrigation systems salt the earth. Forests cut for farmland thin the ecosystems that once balanced them. In time, the carefully maintained order of agriculture produces disorder in the environment. When the balance tips too far, civilizations wither. Entropy does not merely dissolve stone, it erodes the very foundations of sustenance. Energy lies at the heart of this story. Every empire is built on its ability to harness energy flows. Rome expanded through the energy of slaves and animals, the Aztecs through agricultural surpluses, the British Empire through coal and steam, modern civilization through oil, electricity, and digital networks. But every form of energy use leaves disorder in its wake. Forests vanish. Carbon fills the air. Waste piles high. Just as a steam engine cannot be perfectly efficient, no civilization can grow without producing entropy that it cannot fully manage. Collapse comes not only from conquest or corruption, but from the physics of imbalance. This may sound bleak, but it also gives history a kind of unity. Entropy binds us to the cosmos, linking the fall of empires to the cooling of stars. The Roman aqueduct and the Milky Way both obey the same law. In both cases, order is purchased temporarily at the cost of greater disorder elsewhere. In both cases, the balance tips and order dissolves. But humanity is not passive in this process. We resist entropy with every tool we can muster. We carve monuments into stone, hoping to outlast time. We write books, build libraries, erect archives, all in the name of preserving memory. We construct religions and philosophies promising immortality of the soul. Today we digitize our lives, uploading photos, messages, and data into the cloud, imagining permanence in silicon. But even here, entropy waits. Stone erodes, paper burns, servers fail. Digital archives decay with bit rot, file formats become obsolete, and hard drives corrode. Every attempt at permanence is temporary. Entropy is patient, and patience is all it needs. This struggle is visible in culture itself. Languages evolve and die. Of the thousands spoken in antiquity, only a fraction survive today. Myths once sacred are forgotten, replaced by new stories. Music fades as instruments are lost, as traditions vanish. Memory is fragile, and entropy erases even the intangible. We speak of lost knowledge as if it were tragedy alone, but in truth it is entropy's ordinary work. Culture, like stars and galaxies, is temporary order sustained for a time, then scattered into fragments. And yet, paradoxically, entropy also drives renewal. Just as ecosystems regenerate after collapse, so do cultures after decline. The fall of Rome made way for medieval Europe. The collapse of dynasties in China opened space for new dynasties to rise. Entropy clears the stage, allowing new actors to emerge. It is both destroyer and midwife. The law that ensures collapse also makes space for reinvention. Entropy guarantees impermanence, but impermanence allows for creativity. This is why human beings are obsessed with legacy. Knowing that life and culture are fragile, we strive to preserve. We carve names into stone, write epics, build monuments, create art. We archive, digitize, and dream of immortality. But even as we do, entropy shadows us. The pyramids stand, but their limestone faces weather. The Parthenon endures, but as ruin. Digital files multiply, but they rest on servers that must be cooled, powered, and maintained. Every victory is provisional. Every monument is a sandcastle before the tide. If entropy is the hidden driver of history, then our task is not to escape it, but to understand it. Collapse is not failure, it is physics. The challenge is not to conquer entropy, for that is impossible, but to navigate it wisely. To build knowing the building will fall. To create knowing the creation will fade. To love knowing the memory will one day dissolve. This is not despair, but clarity. Entropy teaches humility, but also urgency. The fact that everything ends makes the present matter more. And yet humans have never been content to accept inevitability. We dream of outwitting entropy. We imagine perpetual motion machines, devices that run forever without loss. We imagine civilizations that last eternally, technologies that preserve memory perfectly, futures where death itself is conquered. The laws of physics forbid such dreams, but still we chase them. This refusal to surrender is itself part of what makes us human. In science, these dreams became experiments. Maxwell's demon, a famous thought experiment, imagined a tiny being able to sort molecules, separating hot from cold, apparently revering entropy. For generations, physicists debated whether such a demon could exist. Each attempt to resolve the puzzle revealed deeper truths about energy, information, and the limits of control. The demon turned out not to be a loophole but a reminder. Even knowledge has entropy. The act of measurement, of storing information, generates disorder elsewhere. Entropy always collects its due. Still, the pursuit continues. Physicists probe the reversibility of time in quantum experiments. Engineers design machines of ever higher efficiency, brushing against the edge of entropy's constraints. Biologists explore ways to slow aging, to extend life against entropy's grip. Philosophers imagine futures where consciousness escapes into digital eternity. In each case, the question is the same. Can entropy be resisted, if not defeated? The answer, as far as physics knows, is no. The second law has never been broken, but the attempt to break it has deepened our understanding of the universe. In striving for permanence, we uncover impermanence more clearly. In reaching for immortality, we discover the preciousness of mortality. Entropy humbles us, but it also inspires us. The struggle itself becomes meaningful. This is the bridge to our next chapter. For if entropy shapes not only stars but civilizations, not only matter but memory, then the next question is whether science can truly resist it. Are there loopholes hidden in the quantum world? Are there ways to reverse the irreversible? Or must we finally accept entropy as absolute fate? In the next section, we turn to these challenges. We will explore the human attempts to reverse entropy, the experiments that test its edges, the paradoxes that reveal its depth. From Maxwell's demon to modern quantum mechanics, we will see how far the dream of defeating entropy has taken us, and how, again and again, entropy proves the final arbiter. From the moment entropy was named, it carried with it a challenge. If the second law of thermodynamics says order must always decay, then surely some clever mind could find a way around it. Surely human ingenuity, which split the atom and mapped the genome, could discover a loophole in the universe's cruelest law. And so, for more than a century, inventors, dreamers, and scientists have tried. Their quest has revealed both the audacity of human imagination and the implacable strength of entropy. The first battlefield was perpetual motion. Since the Middle Ages, inventors sketched wheels that spun endlessly, gears that powered themselves, fountains that pumped water without fuel. Their diagrams promised infinite energy, eternal motion, and freedom from decay. Each design, when tested, failed. Friction, resistance, and loss always crept in. Energy slipped away into heat and the wheel slowed. The failure was not just mechanical, it was fundamental. Entropy would not allow such miracles. The dream of perpetual motion machines now rests in museums, symbols of both human hope and entropy's finality. But the story did not end there. In 1867, James Clerk Maxwell imagined a thought experiment that shook physics. He proposed a tiny demon guarding a trapdoor between two chambers of gas. The demon, by observing molecules, could separate fast ones into one side and slow ones into the other, creating a temperature difference. In theory, this would produce usable energy without cost, a violation of entropy. The paradox electrified scientists. Could knowledge itself be a loophole? Could information reverse disorder? For decades, physicists debated Maxwell's demon. Some argued it proved entropy was not absolute. Others insisted the trick was an illusion. The resolution came only in the 20th century, with the realization that information itself has thermodynamic cost. To observe, to record, to decide, all require energy. The demon would need to store data, and in erasing or processing it, entropy would rise. The paradox became a lesson. Not even knowledge escapes entropy. Information is not free. The very act of trying to reduce disorder creates more disorder elsewhere. Maxwell's demon, far from breaking the law, revealed its deeper universality. Yet the human urge to resist entropy persisted. In laboratories, physicists probed whether time could be reversed at the quantum level. The equations of fundamental particles are symmetric. They allow for backward evolution as well as forward. Could entropy's arrow be an illusion born of scale? In rare cases, researchers managed to create small, temporary reversals. Supercooled atoms, entangled particles, and delicate manipulations hinted at tiny escapes. But these experiments required immense energy and precision. The reversals lasted fractions of a second, affecting microscopic systems only. When scaled to the macroscopic world, the arrow always returned. Entropy, though fragile at the quantum edge, remained sovereign in the human realm. Even cosmology entertained defiance. Some physicists imagined that the universe might not end in heat death but in cycles. After reaching maximum entropy, perhaps it would collapse and rebound, resetting the arrow each time. Others speculated about Boltzmann brains, fleeting, self-aware entities emerging by chance from random fluctuations in chaos. These speculations stretch imagination, but none evade the core truth. Entropy increases and order gives way. Whether the universe cycles or ends, entropy shapes the path. Biology, too, has joined the struggle. Aging, in essence, is entropy inscribed in flesh. Cells accumulate damage, proteins misfold, DNA mutates. Scientists pursue ways to slow or reverse this tide: telomere extension, gene editing, cellular repair. Some dream of halting aging entirely, of defying entropy within the body. Yet even here, success would not conquer the law, only delay it. To live indefinitely would still require energy, still generate disorder elsewhere. Immortality of individuals cannot mean immortality of the universe. Entropy would continue its work beyond the body. What these struggles reveal is profound. Entropy is not just an inconvenience, it is the boundary of possibility. Every failure to outwit it illuminates a deeper truth. We cannot create perpetual motion because energy always disperses. We cannot cheat Maxwell's demon because knowledge has cost. We cannot reverse time because irreversibility is written into scale. We cannot escape aging because biology itself is entropic. The second law is not a barrier we might someday break. It is the scaffolding of reality itself. And yet there is value in the struggle. By trying to resist entropy, we have discovered new laws, new insights, new connections. Maxwell's demon opened the path to information theory. Perpetual motion failures clarified the nature of energy. Quantum experiments deepened our understanding of probability and time. The quest to reverse entropy has not freed us from it, but it has expanded human knowledge immeasurably. Entropy humbles us, but it also teaches us. Here we encounter a contrast that defines the human spirit. On one side stands entropy, indifferent, inevitable, universal. On the other side stands human imagination, insistent, defiant, endlessly reaching. We know we cannot win, yet we try. This defiance is itself meaningful. To rebel against entropy is to affirm life, to carve brief order in the midst of decay, to create even while knowing creation will fade. Philosophically, this struggle asks, what does it mean to exist in a universe where entropy is absolute? Does it strip life of meaning, reducing us to temporary eddies in a sea of disorder? Or does it give meaning precisely because we are fleeting? If nothing lasts, then everything matters. If entropy is destiny, then every act of creation is sacred. And so, the attempts to reverse entropy are not failures but parables. They teach us that perfection is impossible but beauty is not. That permanence is an illusion but presence is real. That we cannot escape entropy but we can embrace the significance of resisting it. In this light, Maxwell's demon is not a cheat but a metaphor. The human spirit itself is the demon, tirelessly trying to sort chaos into meaning, even if the universe insists the effort cannot last. Still, questions remain. If entropy rules energy, matter, and information, what about consciousness? Our minds seem to resist disorder, creating coherence, memory, and meaning out of chaos. Are we merely another entropic process, or is consciousness something deeper? Does entropy govern not only our bodies but our very awareness? This is where the story turns next. Having explored the futility of resisting entropy in machines, in physics, in biology, we now confront its role in the human mind. Is consciousness simply another flame that burns through order before fading? Or is it something that transcends entropy's grip? Entropy has shaped our machines, our civilizations, our stars, and our histories. But what about the very thing through which we perceive these truths, our consciousness? If entropy governs everything, does it also govern the mind? Is thought itself just another flicker of order burning briefly before dissolving? Or is there something in consciousness that transcends the law of decay? At its most basic, the brain is an engine. It consumes roughly a fifth of the body's energy, far more than its size would suggest. Every thought, every flicker of awareness is powered by chemical reactions that convert glucose into electrical signals. These signals fire across billions of neurons, weaving the tapestry of perception and memory. But this process is not free. It produces heat, waste, and disorder. The brain, for all its elegance, is a furnace of entropy. The fact that we can think at all is because we are constantly burning through energy. Consciousness in this light is a flame, bright, beautiful, and inevitably consuming itself. Consider memory. To remember is to preserve fragile patterns of neural connections, but maintaining these patterns requires continual reinforcement, constant metabolic work. Memories fade, not only because of distraction or trauma, but because entropy gnaws at them. Neurons die, synapses weaken, chemicals degrade. Just as a photograph yellows and fades, so too does the imprint of experience blur with time. Entropy ensures that memory is not perfect, that awareness is always haunted by forgetting. Even identity is not immune. Who we are is the cumulative order of countless patterns, genetic codes, neural networks, cultural imprints. But all of these are temporary. DNA mutates, cells deteriorate, societies shift. The self, which feels so solid, is in truth an island of improbable order surrounded by the sea of entropy. To be human is to construct meaning against the current, knowing that the construction cannot last. And yet, consciousness feels different from matter. While we can measure entropy in stars or steam engines, what do we make of awareness, of subjectivity, of the inner light that says, "I am"? Here enters one of philosophy's deepest contrasts. On one side is physics, with its ruthless insistence that all things decay. On the other is the mystical vision of soul, spirit, or eternal mind, something that transcends entropy. Across cultures, humans have imagined that while the body withers, consciousness persists, whether in heaven, reincarnation, or some universal mind. These visions promise escape from entropy's grip. Science, however, points in another direction. Neuroscience shows that consciousness is inseparable from brain activity. Damage the brain and awareness changes. Destroy the brain and awareness ends. By this account, consciousness is not a timeless essence but a temporary process. It exists because the brain channels energy, creates fleeting order, and generates entropy in the process. Awareness is not outside entropy, it is born of it. Yet paradoxically, this dependence on entropy gives consciousness its poignancy. Thought is costly, memory fragile, awareness brief, but it is precisely because it is fleeting that it matters. A flame is precious because it burns. A life is meaningful because it ends. Entropy does not strip consciousness of significance, it grants it. Without entropy, perhaps awareness would be static, frozen, unchanging. In such a world, there would be no story, no growth, no learning. Consciousness exists because entropy drives time forward, allowing experience to unfold. And still we wonder, is there more? Could consciousness tap into something beyond the entropic brain? Some physicists and philosophers have speculated that mind might be linked to deeper structures of reality, quantum coherence, informational fields, or even the fabric of spacetime itself. If true, consciousness might not merely be a local process but a cosmic one, entangled with the universe at large. Such ideas remain speculative, but they reveal our longing for transcendence, for some spark of awareness that entropy cannot extinguish. Even if such transcendence remains unproven, entropy itself points toward mystery. Why should the universe begin in low entropy? Why should it allow improbable patterns like life and mind to emerge? Why should atoms assemble into neurons that dream of eternity? Entropy raises as many questions as it answers, and among them is this haunting one. Does the universe itself awaken through us, using entropy to kindle fleeting sparks of awareness. Philosophically, this is where entropy confronts meaning most directly. If consciousness is temporary, are we to despair? Or are we to rejoice that, for a brief moment, the universe looks at itself through our eyes? Entropy ensures that awareness fades, but it also ensures that awareness arises. Without entropy, there would be no arrow of time, no unfolding, no self to ask these questions. Consciousness is not the exception to entropy. It is its expression, its flowering. This realization reframes mortality. Death is not a violation of order but the natural resolution of entropic processes. To live is to burn through energy gradients, to resist disorder locally by spreading it outward. Death is the moment when resistance ceases and the tide reclaims us. But in that temporary resistance, life and mind emerge, shining brightly. Death, then, is not the enemy of consciousness. It is the proof that consciousness was real. Still, the tension remains. Religion and myth offer the hope of eternity. Physics offers the law of entropy. Between them lies the human spirit, torn between despair and wonder. We want permanence, but we are given impermanence. We want eternity, but we are given moments. Perhaps the answer is not to choose one or the other, but to embrace the paradox. Consciousness is temporary, yes, but in its temporariness lies its meaning. And so we return to the flame. A candle burning in the dark does not last, but while it burns, it illuminates. Our awareness, too, is such a candle, fueled by entropy, consuming order, destined to extinguish. Yet in the burning lies beauty, significance, story. We do not escape entropy, but we give it shape. We do not transcend time's arrow, but we ride it with awareness. This leads us to the speculative horizons ahead. If entropy shapes not only stars and civilizations but also consciousness, then what does this say about the ultimate destiny of mind? Will awareness vanish forever with heat death, leaving silence? Or could consciousness somehow persist, perhaps in new universes, new cycles, new forms? These are questions science cannot yet answer, but they frame the mystery of what comes after entropy's final triumph. In the next section, we step into these horizons. We will explore the possibilities of rebirth beyond heat death, of cyclic universes, of multiverse branching. Entropy may dictate endings, but endings may also seed beginnings. Perhaps, just perhaps, the story of entropy is not only about decline but also about renewal. If entropy is the law that drives the arrow of time, then its logical conclusion is the heat death of the universe. A cosmos stretched thin, every gradient erased, every difference smoothed away. It is an image of profound stillness. No stars, no galaxies, no life. Only silence, uniform and eternal. For some, this is the ultimate nightmare, the end of story, the erasure of meaning. But humans are not content to accept such finality. Across physics, philosophy, and imagination, thinkers have dared to ask, what if heat death is not the end? What if entropy itself hides new beginnings? One of the oldest alternatives is the idea of a cyclic universe. Long before modern cosmology, myth spoke of eternal returns, the phoenix rising from ashes, worlds destroyed and reborn, time looping endlessly. In modern physics, this idea finds resonance. Perhaps the universe does not end in heat death but collapses in a big crunch, gathering all matter back into a singular state. From that singularity, a new Big Bang might erupt, resetting entropy and starting the cycle again. Each universe would be a breath in a cosmic rhythm, expansion, collapse, renewal. Entropy increases within each cycle, but the cycle itself is eternal. Death gives way to rebirth. Yet observations complicate this dream. The universe's expansion is not slowing but accelerating, driven by dark energy. If acceleration continues, collapse may never come. Instead, galaxies will drift apart, stars will fade, and heat death will proceed unchallenged. The cyclic model remains beautiful but perhaps out of reach. Still, some physicists imagine alternatives. If dark energy changes its nature, the expansion might reverse. If unknown forces shape cosmic dynamics, cycles could still occur. The question remains open, and with it, the hope of renewal. Another possibility is the multiverse. If our universe is only one bubble among countless others, then heat death here may not be the end of all things. Beyond our horizon, other universes may bloom, each with its own laws, energies, and stories. Some may be newborn, brimming with low entropy. Others may be ancient, drifting into silence. In this view, entropy's victory in our cosmos is only local. The multiverse as a whole may be infinite, eternally spawning new regions of order. We may live in one chapter of an endless library. Our entropy is real, but the story continues elsewhere. Even within our own universe, some imagine ways entropy could be reset. Black holes, once thought tombs of information, may instead be wombs of creation. Some theories suggest that inside black holes, spacetime may pinch off and create new universes. If so, then each collapse seeds another cosmos, each with its own arrow of time. Entropy here is not destruction but transformation. The death of one universe is the birth of another. We may be children of such a process, our own Big Bang the echo of a black hole in another reality. Quantum theory also offers strange horizons. In the many worlds interpretation, every quantum event branches reality into multiple outcomes. If so, then entropy's increase in one branch is balanced by decreases in others. The arrow of time may not be singular but branching, fractal, endlessly diversifying. In such a multiverse, endings and beginnings coexist. While our path leads toward heat death, other branches may flourish with order anew. Entropy here is not absolute but relative to perspective. These speculations stretch imagination, but they share a common theme: refusal to accept entropy as the final word. Humans, faced with cosmic silence, dream of continuities. We imagine cycles, rebirths, branches, and multiverses. Even if entropy rules, we hope there are deeper laws beyond it, patterns that turn endings into beginnings. But here lies the contrast. Science gives us no guarantees. The second law of thermodynamics has never been broken. Every observation confirms its sovereignty. Heat death remains the most likely fate. And yet, speculation reminds us that our understanding is incomplete. Dark energy, quantum gravity, black hole physics, all remain mysterious. Within these mysteries may lie surprises. The future of the universe is not yet written in full. Philosophically, the tension between despair and hope defines our relationship with entropy. If heat death is absolute, then meaning lies in the present. The fleeting beauty of stars, the brief blossoming of life, the temporary flame of consciousness. If rebirth is possible, then meaning extends into eternity, the assurance that order will always rise again. Either way, entropy forces us to confront impermanence and possibility. There is also another way to see the end, not as silence, but as transformation into something beyond comprehension. When entropy erases gradients, when distinctions vanish, the universe may not end in nothingness but in unity. All differences dissolved, all structures merged, all separations gone. To us, this looks like death, but perhaps from another perspective, it is fulfillment, the cosmos returning to oneness. In this sense, heat death is not the erasure of meaning, but its transcendence. The story ends because the story becomes complete. Mystics across cultures have spoken of dissolution into the infinite, the return of the soul to the source, the merging of the self into the absolute. Science, describing heat death, speaks in colder terms: equilibrium, uniformity, entropy maximized. Yet the resonance is striking. Both describe the end of distinctions, the fading of individuality, the merging into the whole. Perhaps entropy, in its final triumph, is not only physics but philosophy, the material echo of spiritual return. And yet, as humans, we cannot help but resist. We crave renewal. We imagine that beyond entropy there must be another chapter. This longing itself is meaningful. It reveals that we are creatures who cannot live on silence alone. We require story, cycles, hope. Even if heat death is true, our need to imagine beyond it gives our present life shape. To speculate is to affirm our hunger for meaning, even in the face of inevitability. And so, beyond heat death lies both despair and wonder. Despair, because the universe may end in silence. Wonder, because in that silence may lie seeds of renewal, or the fulfillment of unity, or the branching of worlds we cannot yet imagine. Entropy does not answer these questions, it provokes them. It pushes us to ask what lies beyond endings, what lies beyond time, what lies beyond the story itself. This is where science and philosophy meet most intimately. Science tells us entropy increases. Philosophy asks what this means for us here and now. Perhaps the answer is simple. Whether the universe ends in silence or renewal, we live in the precious middle, where order blooms briefly. The question is not whether entropy can be reversed, but how we live knowing it cannot. From the first whisper of entropy in cooling steam to the cosmic silence of heat death, we have traced the law of disorder across every scale of reality. It governs machines, memories, civilizations, galaxies, and even the fire of our own awareness. At each turn, entropy has seemed like a thief stealing permanence, erasing beauty, dissolving what we love into dust. But as we stand at the close of this journey, another truth emerges. Entropy is not only the destroyer. It is the sculptor of reality, the silent hand that gives shape to existence. To fear entropy is natural. It reminds us of endings, of death, collapse, silence. Yet without it there would be no beginnings either. Without entropy, time would not flow. The arrow would not move. Stars would not shine, life would not bloom, consciousness would not awaken. It is entropy that ensures history unfolds as story, not as static tableau. It is entropy that makes each moment distinct from the last. Think of a sunset. Its beauty lies not in permanence but in impermanence, the fading of light, the colors dissolving into night. Think of a cherry blossom. Its glory comes not because it endures but because it falls. Entropy is the reason beauty matters. It tells us, nothing lasts, so everything matters. The fragile is precious precisely because it is fragile. We carve monuments and build archives because we long to resist entropy. And yet the pyramids erode, the libraries burn, the data decays. At first this feels like tragedy, but perhaps it is also gift. If everything could be preserved, nothing would carry urgency. If memory were eternal, choice would lose its weight. If love were infinite, it might lose its fire. Entropy makes life urgent, memory poignant, love fierce. It shapes the very intensity of being alive. There is a strange comfort in this. Entropy equalizes all things. The emperor and the peasant, the star and the stone, the galaxy and the grain of sand, all move toward the same dissolution. We resist, we build, we imagine permanence. But in the end, we all return to the great unfolding. To live with entropy is to live with humility, to recognize that we are not exceptions but participants in the universal rhythm of change. And yet this is not resignation. To see entropy as sculptor is to see that our resistance, though temporary, has meaning. Every act of creation, painting a picture, planting a seed, speaking a word of kindness, is a flare of order in the dark. It may fade, but while it burns, it illuminates. The fact that it will vanish does not diminish its beauty. It enhances it. This reframes the way we understand our place in the cosmos. We are not defeated by entropy. We are made possible by it. We are temporary eddies in the current, whirlpools in the river of time, fleeting patterns in the great dispersal of energy. To despair at this is to miss the miracle. The miracle is not that things fall apart. The miracle is that they come together at all. That atoms assembled into stars, that stars forged elements, that elements formed planets, that planets gave rise to life, and that life became conscious enough to contemplate its own fragility. Entropy, then, is not only physics but philosophy. It invites us to shift our gaze. Instead of clinging to permanence, we can embrace impermanence. Instead of fearing endings, we can cherish beginnings. Instead of lamenting decay, we can see it as the price of beauty. Entropy whispers not only of loss but of meaning. And so, as we close, imagine the universe as a great story. The chapters are written in stars and galaxies, in civilizations and memories, in the brief spark of consciousness. The story begins with improbable order, unfolds through the growth of complexity, and ends in the silence of heat death. But the ending does not erase the story. The story is precious precisely because it ends. Entropy gives us not eternity but narrative, not permanence but significance. What then should we do with this knowledge? We should live fully in the fleeting. We should love without hesitation, create without fear, embrace the fragile, and honor the impermanent. Entropy guarantees that nothing lasts, but it also guarantees that this moment, here and now, is unique and unrepeatable. To live well is to honor that uniqueness. Perhaps the greatest beauty of entropy is that it humbles us into gratitude. Gratitude for the stars that burn, knowing they will fade. Gratitude for the civilizations that rose, knowing they would fall. Gratitude for the minds that awaken, knowing they will sleep. Gratitude for the fragile order that makes life possible, even as it dissolves. Gratitude for the fact that, against overwhelming odds, the universe came together into story at all. And so we return to where we began, with castles crumbling, stars burning out, and civilizations collapsing. Yes, entropy will claim them all, but within their rise and fall lies the essence of reality, transformation. The castles may crumble, but they were built. The stars may burn out, but they shone. Civilizations may fall, but they dreamed. The whisper of entropy is not only a whisper of endings, it is a reminder to cherish the miracle of beginnings. In the end, entropy does not diminish us. It defines us. It is the canvas upon which existence is painted, the rhythm to which life dances, the arrow that makes every moment matter. The universe is not built to last, but it is built to shine briefly and brilliantly before returning to silence. And in that silence, perhaps, lies not despair but wonder. For everything that falls apart once came together, and that coming together, against the odds, against the tide, against the certainty of entropy, is the most beautiful miracle of all.